Good day and welcome to this Saturday's technical session of the CNPS. It's the 17th of January 2026. My name is Ian Cowan, and as usual we'll be proceeding with a talk from one of our invited speakers. I noted, by the way, earlier this morning here that on the 17th of January, today's date, 2020, prohibition was introduced into the United States of America by federal decree. Now, so that's an interesting coincidence, if you like. It was repealed in 1933. But unfortunately, if I may say so, worldwide, there is still a prohibition on questioning the fundamental theories of physical science. Well, this society, the CNPS, is not party to that. And we are actually encouraging people to be very critical and criticize all these ideas. So you're certainly not prohibited from doing that. And I think today's talk will be leading in that direction. Now, before getting down and introducing our speaker and so on and so forth, I just beg your indulgence for 1 minute or so. That's all it'll take. It's basically just about the running of the CNPS, which we're not prohibiting people from questioning all ideas which are currently accepted and presenting it to us. In fact, we're encouraging that. But the society is such that the income from membership dues doesn't actually cover the running costs of the society, including all the software and platforms we need, including the StreamYard one we're using today. So last year we had a fundraising endeavor which helped to bridge the shortfall. And this year we've launched one as well. So if I just play this video, which I promise will not last more than a minute, given by the president of the John Chappell Natural Philosophy Society, David de Hilster. Let me see, just get it up now. And then we'll get into today's business. So here goes, ladies and gentlemen.
Hello, everyone. I am David de Hilster, president of the CNPS, and this is our annual fund drive. First, I want to thank all of those who have been paying their annual and monthly memberships through our automatic membership system. It is greatly appreciated. Since 1994, this group has been pioneering support for critical thinkers outside of mainstream science, and we continue to do so through our virtual presence, through our Saturday morning live streams, and our website discussions. Since last year, we have cut our expenses down to something reasonable for our current membership. In 2026, we hope to implement the Discourse Discussion Group as our primary discussion software. Our current website system, in my opinion, is not ideal. We hope to change that. To donate, you can go to fund.naturalphilosophy.org and donate whatever amount that works for you. Your contributions are greatly appreciated. Thank you.
Very good. Fund.naturalphilosophy.org, and all contributions will be gratefully received. Now, for today, we have a very interesting lecture given by Jeff Cook. I don't think many of you probably will know Jeff Cook, but he might be able to say a word or two about himself when he starts his presentation. And the subject is Annarithms and opponents. Now, I've had a quick look at some of the slides. They're quite mathematical. And for my part, I think mathematics has a very important role to play in physical science. And from some of the comments maybe made in recent times by some of us, including myself, one might have been led to the conclusion that we're all dismissing mathematics. And that's not true. What we have been doing frequently is dismissing the sort of ivory tower thinking, which just fiddles around with mathematics without regard to experimental evidence, and then figures out some theory, some physical theory, and then defends it to the end of the world. So mathematics has a very, very important role to play. And in fact, I think to a certain extent it's neglected. We tend to talk a lot, waffle a lot, and we use language. Language is it's fine for writing prose or poetry, but when you're describing physical science, it's a very inexact means of communicating information. So really, mathematics is the ideal tool. And Jeff will be going into some interesting mathematical techniques that he's developed in regard to mathematical operation useful for physics modeling, for modeling physical systems. The spiel is that he has discovered a basic and fundamental arithmetical operator not previously described in the literature. So that's important. It's unique. It's new. It is centered on the process of repeated self-division and seems to be a very natural approach to a number of physical and mathematical processes, including exponential decay, propagation of light, fractal growth, and more. It does also seem to be a powerful new mathematical tool for exploring theoretical physics models and alternative theories. Okay. So the basic system which we propose and we normally adhere to is that we'll give the floor to our speaker, Jeff Cook, today. And we might invite him to say a few brief words about himself and his own experience and what he's working in. Because many of us don't know him very much. And then Jeff will then proceed. Now, he has slides and quite a number, I think 49 slides. I hope he gets through them all. But so he can probably project those himself. And I'll just ask our audience to bear with us again for a minute or two, because we just want to get them up. In the event that Jeff is not able to do that, I have the slides here on my system and I can do it. So we're just going to spend a moment getting those up. And then Jeff will be spending up to an hour. That isn't very tightly fixed. If he wants to spend an hour and a quarter, that's fine. If he wants to spend 50 minutes, that's fine. But roughly an hour, so that we'll have roughly an hour or a little less for questions and answers. Now, the form that the Q&A takes is that people will be posting their comments. None have come in. Well, actually, I'm wrong. A couple have come in, but they're just trivial things on is StreamYard working or something on the social media, because we have people participating through Facebook and YouTube. And please, I know you converse. We use the system to converse between yourselves, and you're talking about your own experience, and that's fine. But if you have any specific question for Jeff, just put that. Say question for Jeff, or maybe Ian. Would you make sure that's addressed so I don't miss it? And then we have a number of people. I see we have a number of people already logged in. We may have more in the green room. And what we'll do is we'll have a more detailed discussion, with to and fro discussion between Jeff and our participants in the green room, and then we'll give Jeff an opportunity of maybe summarizing. In the light of any questions which have arisen, and maybe any other points which he didn't cover in the talk, but points which were prompted by the Q&A and discussion. And we'll close the meeting then. And as you know, and Jeff will know, that there's an online recording system in StreamYard. So as soon as this lecture finishes in 2 hours' time, it will be on the John Chappell Natural Philosophy YouTube channel. So that's it. So without further ado, I'm going to bring Jeff up. Now, let me see. He had some teething problems with the camera. Why isn't it showing it now? Because I've got a black. Can you hear me, Jeff?
I hear you well, and I see you well.
Excellent, we can hear you. Perfect. But unfortunately, even though the little icon is showing your visage, all I have now on the screen is blackness.
Okay.
Is that what you're saying?
No, I see myself.
I
see myself and you sitting next to each other. So I don't really know what's going on.
Okay. Well, I'm going to bring one of the people up in the green room and just ask him.
Yeah, sure.
Does he see? So I see James Keane is there. James, sorry to bother you. Can you see Jeff's photo, or is it black?
No, it's black, Ian.
Yeah, I thought so. It's not just me. Okay, thank you very much, Jim. So I just wanted to check that. There's a problem in transmitting this, Jeff. And I don't understand
it's
why.
really weird because I see myself on StreamYard talking to you.
And I see you on the little icon as well.
Huh.
So,
So if you see me, then it's not on my end. I don't know what to say.
but nobody here in the green room can see you either. So it's not just me.
Well, I think the most important thing is if you can hear me well, and then I can present the
true.
slideshow, and I think the rest kind of will fall
Yeah.
into place. I am sorry. Don't know what to say.
It is possible that as I bring myself down and I give you the entire floor, it may resolve itself.
Okay.
But so what I'll do with your agreement, Jeff, is I'll disappear. Now, what that means is I'm muted, and you know, if something urgent arises and I say something, it won't be heard. But if you say, Ian, there's a problem, would you come back? I'll come back. It'll only take me a moment to come back. And
the first thing I'm wondering is how do I share my presentation?
Yeah, quite so. That's what I was going to say. So what we'll do actually is we'll go through the process. We can go through it now. So we have I think we should do that actually before we give you the entire floor. So let me remind people how that's done. Do you see, Jeff, at the bottom of your screen, a little banner with, say, a microphone icon on the left, and the next one is a camera icon, and then the third one is a screen with a plus in the middle of it? Do you see that?
Yeah, it says present.
Quite. Well, if you press the middle one, the screen with the plus on it, it will say share screen at the bottom. Do you see that?
Yeah, I'm getting there. Okay.
Share screen.
All right. I think
it should be intuitive, but it's a little tricky. I just happen to know it from experience. So it'll then say at the top what you want to share. So you say entire screen at the right-hand side top. Do you see that?
I did, but it's just showing up as black. So I think you're going to have to share the presentation.
Ah, okay.
Yeah, so now I'm seeing that black. So as soon as I shared it, it disappeared.
It's something, you see, Jeff is actually using two video systems, his computer, which was giving us a problem earlier, and he's using his phone. So I think that may be the problem. But anyway, that's no problem. Yeah, it's black. It's black.
Yeah, just if you could share the PowerPoint on your
I'll share the PowerPoint. So what I'll do is I'll give you the floor, and you can say a few words, and then when you're ready, just say, Ian, share the PowerPoint, and I'll do that. Okay.
Okay, that sounds good.
I'm going to let you introduce it without interruption. So the floor is yours now.
All right. Well, good morning, everyone. Good morning, Ian. I have done a number of presentations, about 4 or 5, with NPA back when you guys had that name. I think maybe one in the early years, but I haven't met you, Ian. So some of the people may remember my work from back years ago. So I kind of first became understand about the NPA through Greg Volk at a Tesla Tech conference, which I met him at, and we hit it off. And then through him, I met Dennis Allen, and we have co-written a few papers. So yeah, I guess we could share and mentioning about mathematics and experimental physics. I would say that by nature I'm more of an experimentalist, and I definitely prefer building things and seeing what really works. Yeah, because it can all look good on paper with math, and then you try to make it happen in reality, and reality just denies it. So I'm a big fan, I guess we would say, of experimental physics. But I do love math and some even math without anything to do with physics, number theory. I'm fascinated by it, and so I think there's a lot of crossover in between the two. And so what I found here is something I think that most people, while it can go very deep on the surface, it's elementary, even trivial, and probably why it's been overlooked for so long. But it is very useful in solving a large number of problems, particularly most of the problems that we have that we're looking at, unsolved problems today. They usually are centered around infinities, singularities, and all of that. And I think you'll be interested to see how this can be handled with this. And it's just an elementary operation that we've just been lacking in. And I'm just going to kind of go through it. You could share the first slide, and I'll just kind of say next slide each time. So if you want to kind of put that first
well, let's do that. It'll just take me a moment because I'll have to go through what we just tried with you. Yeah. And then when we're up, you just say next slide, next slide. So let me just
Yeah,
see.
exactly. And I'll probably go pretty quick because, yeah, there are like 50 slides. So
Yes, indeed.
a lot of them are just, I always want to point out one part of each page. I don't need to go over all of it.
Let me see now. So, well, wait a minute. First of all, I have to put it up. No, that's it. My screen is shared now. And just tell me, Jeff, if you're not seeing it. Now, but what I have to do is I have to get the slides up because that's what I want to share. So let me just do that.
Yeah, and just start from beginning of first slide.
Maybe I get rid of these things at the no, sorry, this way. It's slightly better if I can.
You go up to slideshow.
No, see that slideshow.
Yeah, that works. Okay,
am I at the beginning now or not?
No, I would go up arrow, a couple more.
Back.
Up arrow should work.
Up arrow.
Keep going. Right there. So that's the first slide. That's the first slide. Okay, and then you can just do down arrow for each slide after that. All right, are you hearing me okay then? Is my mic?
I can hear you perfectly. Can you hear me?
Yeah, we're good.
So I'd better stay on, actually. Normally I mute myself. I better stay on because I may have a problem and I might want to.
Okay, yeah, it gives me something useful to look at too. So it's okay. All right.
I'll try not to cough too much.
All right. So I'll try to get through it. There's really only 3 simple rules with this to understand it all, and anyone can take this, even if they come on late and miss anything with this presentation. You just copy those 3 rules at the very end, plug them into ChatGPT, and it will walk you through the rest because it goes deep fast. But like I said, on the surface, it's so simple that it's very easy to overlook. So let's just go to the first slide. All right, so there's 3 things that I want to present here. One, the concept of self-division, weights, which is nothing new. It's kind of the same thing as Laplace damping, where you're basically causing some function to converge faster by adding weight to it. And you can do this from both sides of an inequality. But I do want to touch on it because it is very useful. And then the last is the rate incommensurability principle, or rate incommensurate principle. And I'm going to go over those. The third is something found from the first concept. So, but it's really, to me, one of the most fascinating things come out of it. However, I'm pouring out more papers than I ever thought I would be able to do. I only uploaded 4 to my account at ResearchGate, but there's a large number of stuff on my desktop. It's just more information coming. So I thought I really need to open this up to other mathematicians and physicists and get people working on it, because it is really a powerful tool once you get your head around it. Okay, next slide. All right, so the concept is of self-division, and what I mean is, like, well, I'll kind of get into it. It's kind of something like exponentiation, which is self-multiplication. Next slide. So this is kind of way we've been looking at math. Is everything is reversed.
Sorry, this was upside down.
Yeah, no, this is intentional.
Okay.
So this is the way we've been looking at math. It's been in a lot of equations where it's reversed, it's inverted, and it's offset. And we look at it and think we're understanding it, but the reality is, turning it around in this right way, it makes the equation of what's going on with a certain equation in physics or anything a lot clearer. Next slide. So go ahead, next slide, Ian. Yeah, so what this does, it just turns everything around and offsets it. So let's go back. We skipped through a few slides.
Go back.
Yeah, down. And then one more. Right there. So what I'm going to do is I'm going to show how to take these equations and kind of reverse them, invert them, and offset them, and to show you what's going on. And really at the heart of it is this concept of self-division. Now, self-division is occurring in nature everywhere. It's occurring in physics. It's occurring in biology, and in mathematics. Light does this, and it's something that we don't even know is going on, and but we see it everywhere. And once you see it, it's very hard to unsee it. So let's just take some self-division. What you have is, so just in terms of biology, it's the same thing. It can be a chemical reaction at the very onset. where a sperm meets an egg, and there is a significant amount of electricity and energy put into that initial reaction. But chromosomes are crystals, and they only grow so fast, and the energy being put in is coming in faster. And so the storage mechanism of that is to cause them to split. So these cells and the chromosomes split, and then they continue to grow, and then they split and they continue to grow. That process is governed by a very simple mathematical rule. And it's amazing that it happens when you look at it until you realize it's happening it's as simple as 1 + 1. So let's go ahead and do the so the ultraviolet catastrophe, which most on here will be familiar with. Well, we're going to get into it in a little bit. There's this concept of what is the mechanism stopping runaway growth in the universe. There is something, and we saw it with the UV catastrophe, where it should look like the energy of light should go up, infinitely at a certain point, and we'll get into it. But in reality, is it just naturally comes down. We could think of this in terms of population growth as well, or any kind of growth, where it seems like it's going up exponentially and all of a sudden comes down. What is that mechanism? So that's what we're going to kind of, that mechanism is self-division. And I'm going to kind of show what it looks like mathematically. Go ahead to the next slide. All right, and so example of how it is the process, it's being used in terms of energy storage, even within an electron, or within a capacitor, electromagnet, where there's more energy going in than coming out, or it's going in at a different rate, and then it gets stored. And so just example with the human being, so the average 2,300 calorie diet, that's enough energy if one lives to be 80 years old to the power average household for 7 to 8 years. That's how much energy is going in with that initial reaction. And so as long as there's so crystals grow from taking up external material, so humans do too. We call it food. And so as long as there is that external material around us, then that chain reaction will continue to go on and on and on. So the point of it is that it does kind of stop runaway growth. And let's go to the next slide and bringing it more into physics and math. So this originally came about 15 to 16 years ago. It's kind of like something just like a napkin doodle. I was sitting there, I was bored, and let's just see what would happen if we just start dividing a number by itself, just like, a number multiplied by itself, x times x times x, and what would happen. And if we do x divided by x, x divided by x, and then so on. And then let's start to kind of add some rules to this and see what just follows from it naturally, like Euler did with exponentiation. And that's exactly what it was. When I had found it, it was not very exciting. I couldn't see any useful application for it, largely because it can be reduced back to exponentiation. But so I kind of let it sit there for 15 to 16 years until this summer. And so a lot of what I'm going to say is new to me as well. And I know enough about it to discuss it, but I may not be able to answer all questions that come my way, because it's very fascinating. It takes a different way of looking at it. But I used to have a website, and so if you were to have clicked on that little files and links there, you would have found the file. You could next slide here. It's just showing where it was. So I know some people may have been a website. Website's not. Slide. Yeah, next slide. Yeah, so there was a little link there that kind of had where I jotted down my idea. And you can do next slide too. You can just skip over this. And but there's many results that I'm coming upon. If you go to ResearchGate, Jeffrey N. Cook, you'll just see there's a lot of things up there about prime dynamics and probabilities, L series of electric curves, the rate incommensurability principle, which I'm going to discuss, and it's just coming pouring out like a fire hose. So definitely I'm going to kind of go over it, but they're solving some very, very big problems that have not been solved for hundreds of years. And so I think that's why it's useful. But it all came about by teaching my daughter basic division. then it came back to me, this concept, and then went into Chat GTP and said, can you find anything that where this has applicable? And it like started jumping up and down. It was very excited about this and found many applications. So I can't change the slide to the next one. Are you there, Ian? Let's go to the next one.
I just disappeared for a fraction of a
No,
second.
that's fine. That's fine. So it started with this. So my daughter brings home this picture, which she got wrong, a math problem with pizza slices. And so I said, it made me realize that she's right in this concept, and we're teaching people wrong of what division is. We're thinking of it in a different way, and I can prove it's wrong. So average person will look at this, and the question is how many times did we divide this pizza? So you can't really understand self-division if we don't understand what is division in itself. We know how to use it, but what is really going on? So how many times we divide this? Some people may say 4. Some people may say 8. My daughter says none. And she's right. If you flip to the next slide, I'll show you why. So, and then the next one again. And because the whole is equal to the sum of its parts by definition, the whole pizza is still there. We've just partitioned it. We haven't taken anything away. So a kid will look at that and say, well, that's a whole pizza right there. I don't care how you slice it. There's nothing taken away. And so, next slide, please. So if we divided it 8 times, then why is the whole pizza still there? The next slide. And this is kind of a ridiculous, this just kind of shows the nonsense of it, is 8 times 1/8 is still 1, still whole, but that does not equal 1/8. So we're not dividing here. I just bring that up because I want to give this new concept or this different way of looking at it in terms of what we're doing here is partitioning, and it's a very big difference from actually performing the operation of division. Next slide. And next one again, that's just kind of what I just said. And then this is important too, because what happens is I think we really need to stop thinking of division in terms of quantity. We need to stop thinking of multiplication in terms of quantity. It may be useful in terms of like, x times x times x is an exponent, of b times. But what does it really mean when we have e to the power of pi I? What does it really mean when we have, how do we add, parts of pi? All of these concepts are become ridiculous in terms of multiplication. There's a few cases where we can reduce multiplication and division to quantities, but really it's much better describing in terms of scaling, in terms of growing or shrinking or contracting. And next slide, please, and I'll kind of show why. All right, so at this point, now you can say, okay, we have divided the pizza in 2 because there's only a half a pizza there. So if we perform the operation of division, then we should only have a half a pizza. And it seems very basic, and it is. But let me get my glasses on so I can see all of this here. At this point now, we can say, well, a diameter of a circle divides, or a diameter divides a circle by 2. Before, we couldn't actually say that. So we didn't really divide anything. So we still had the full circle. But quantity division, n equals, the natural numbers 0, 1, 2, 3, is really only meaningful beginning at magnitude 2. And this becomes very important for what we're going to show. And I'll show you what I mean. Take a times a. How many times do we perform that operation of multiplication? Once. Yet we call it a to the power of 2. And so the same thing, it's kind of that offset begins in the first place. Same thing as how many times do we divide the pizza? 2. So when you're going to see this offset appear naturally in this next case, because we're already kind of mixing the operation with the power or the number of times the operation is performed. So let's go to the next slide, and it should become very clear here. So at a basic level, we have to ask, what is the operation acting on? So we're talking about partitions before. So let's partition 60 apples into 2 bags. Okay, let's just say they're all equal in all other respects. Multiplication, in terms of addition, it's like it destroys the partition. It annihilates it. So 2 bags times 30 apples equals 60 apples. What happened to the bags? We don't know. It's no longer, it didn't come out of the operation. Or we could say that the operation ignores the partition altogether. And I think that's the right way to do it, which is why I would say when we did that pizza, we're either partitioning or we're dividing. They're not the same thing. And so this is what I want to kind of look at in terms of, and partitioning only really becomes relevant when we're talking about multiplication and division in terms of quantities. So the quantity is the useful part of these operations, not the partitions. And so that's why the pizza was, we partitioned the pizza, but we'd actually perform the operation of division. So you could think of it, the best way I like to think of it is like a piece of wood. You burn it and the carbohydrates go off into space or in the atmosphere, wherever they are, and the ash remains, and that's the residue. And that's going to become very important because it is actually at the heart of Euclidean division too, where you have the remainder after division. And this becomes very important for a lot of what we're going to talk about, where it's all about residues, because this is where all the constants, the dimensionless constants, come up in physics and mathematics. Pi is example, square root of 2 is example, the Euler-Mascheroni constant is example. They're all kind of residues after the operation is taken or reduced to the lowest possible value, which I'm going to kind of explain a little bit more. Okay, next slide. All right. So in doing this, since we can reduce multiplication to addition, we can sit there and look at it, and we can say, or we can kind of say, okay, we're multiplying 2 bags, and we get a quicker way of adding 30 apples plus 30 apples by multiplication. But it's not the way the operation is intended, and that becomes clear. So a lot of people are familiar with repeated succession, but addition can be actually described in terms of repeated succession. So one passes along, and another number passes along, and then we can consider adding it. So addition can be repeated to succession. And let's skip over. Are you able to see my mouse moving, Ian?
No. That's
Okay,
probably because my mouse would move.
Okay.
See, I have control.
Yeah, so I see your mouse and my mouse. Yeah. Okay, so that's okay. I'll just kind of describe it. If you look where it says addition, skip over division and go to multiplication. Multiplication can be described in terms of repeated addition, and you skip over the question mark, we get an exponentiation. That can be described as repeated multiplication. But again, it doesn't really kind of explain as how many times are we repeating multiplication of when you have expressions like e equals pi I, or the power of pi I. So it can be reduced. And the same thing for subtraction. Go back to the bottom. We can do subtraction with addition and inverse. And we can also reduce division to multiplication plus inverse exponent. But if we keep on looking at this, it does seem that there's this missing gap here in the order of operations, because what makes each of these unique is the order of operations. So if you have an equation and you want to, you can't just start divide by x to bring it to the other side. If you have something in powers, you have to do the order of operation is do exponents first, or parentheses first, and then exponents, and then multiplication, and then division and addition. And that is really kind of what makes these individual unique operations, because they all can be reduced to one another or to one or the other. It does, when you get there, then you are missing something fundamental. Now, just to know how long we've been missing this fundamental, if you believe it will be, and I think you will soon, exponentiation was done all the way back to ancient Egyptians. And it was formulated in a more, permanent way with Euler, and with when he started to define it, logarithms and all of this. And we use it now, if we were taught it at a young enough age, we use it second nature to us, to kind of how to manipulate an exponent and so on and so forth. But it really was something that doesn't go back too far. The concept goes back to ancient Egyptians, but never, and I kind of trying to research, is there anyone that even dabbled in self-division? And I can find zero record of it, not through any of the AI, assistants and all of that. They can't find any record of anyone ever doing it. And I think the issue is because it's just, why? That's the first thought I had is, why do it if everything can be reduced to exponents? But there are some reasons why we should. So let's go ahead and next slide, and I'm going to show you what it does here. So we're going to give this operation a name. A divided by A divided by A, B times. All right, we're going to give that a name. We call it submission. Why? Because if exponential, it's the inverse of exponentiation. So if we raise A to B, A to the power of B, then submission is we lower A to the submission of B. So we're just going to say the opposite of raising something to power is something submitting to something. And I have two different symbols here. If you look at submission, just A sub B is great, except a lot of functions have subs and it has a lot of different meanings. So you may double it up on notation. So you can use the A to the raised down arrow of B, and that can mean it, or there's some other ways too. But this is just kind of, we're going to give it a name. We're going to call it submission. So that number B, or that variable B, it's not an exponent anymore. We're going to say it's an opponent. An opposite of X is something opposing. So next slide, and here's some of the rules for it. So when you do this, if you look at just A divided by A divided by A, the first time you do A divided by A, it's simply 1. The second time it's the inverse, 1 over A. The next time we're getting this offset by 2, which is what we talked about. So the opponent, or the A submitted to X, is identical to A to the power of 2 minus X. And it's this offset 2, or it can be offset 1, is kind of where you see all of this. You see a lot of it in physics, some value to the power of X minus 1 or 1 minus X. And all of that, whenever you see that, now you can look at it and say, that is from self-division. That is not from self-multiplication. And then if you take this and follow the next logical step, is we need something to reduce that opponent back, some operation. And so the logarithm kind of reduces an exponent. And so log means to record or to register something. So we're going to actually remove that registry. So we're going to call it, so I use the root of annihilation, so we're going to call it annarithms. We're basically going to remove that record. And so the reverse of that, it has this, it says defined as a colon equals, but it's not actually defined. It's the logical result of the operation that would do it. It would end up equaling 2 minus log. So annarithms of anything is going to be equal to 2 minus log of that thing. And so we have this offset. Now, there is a balancing point when multiplication becomes division, and that is at 1. So 1 times 1 is 1, and 1 divided by 1 is 1. Multiplication and division become the same thing at this point. There's also this equilibrium point between exponents and submission, and that is at the square root. So A to the power of 1/2 equals square root of A. That is identical and equal to A submitted to 3/2. So this 3/2 is very, very important. Shows up a lot of boundary conditions and infinities, and I'm going to go over a few of them. So it's very fundamental. It's as common as the square root of a number because they are identical at that point. So the crossover often occurs when you have something going from exponential growth, and all of a sudden it starts to taper off. Nobody knows why is it tapering off. You have to go through and add all of these quanta and all of these other variables and this whole other model, when in reality it's just arithmetic. It's just crossing over into submission because they are equal at that point. And I'm going to show that here. Go ahead, next slide. You can see that with the ultraviolet catastrophes. So you had this prediction by Rayleigh Jean. I don't know how to say the last name in French, but Jeans Rayleigh.
Jeans, he was British, certainly.
Okay, so Rayleigh Jeans then, and he had this prediction, well, that this energy should go up to infinity, but in reality, that's not what was matching experimental output. So you have Vienne, who actually kind of described the decay, which is accurate, after a certain point, and that dividing line is at 3/2, and it is Planck who came and balanced it. Well, his paper, I think, was like 8 to 9 pages long and had to introduce quanta, which he didn't really believe even really existed. And here it's going to be described with 3 simple equations and a simple x tweet, and a very, very simple solution that describes the same thing, and which is at the bottom of this page. So that growth is because the exponential growth that begins crosses over at the point of 3/2 and then starts to become self-division. In fact, the majority of what is going on is self-division off to infinity. It's only, we're talking exponents, for a very small point of x, a small region within x. So this is kind of what I'm talking about. It is that crossover level, is that which balances unbounded growth in nature. Happens with gravity, it happens with you name it. So I decided, okay, let's see how far we can take this. Can we do the next slide? So I decided to first apply it to Eric Weinstein's model. So he has a model. I'm not saying it's particularly popular, but it's kind of interesting. And he certainly seems to be covering all bases, but he's missing one. So a lot of complaints he has is that he doesn't have a balancing mechanism. So his concept of the universe is that it is not expanding, but it's flowing through something like the shape of a horn. Whatever you want to say about that, it doesn't describe the mechanism of where there's this balance between expanding and constraining flows, which do happen. And so he just kind of, I don't know if he doesn't care about it, or if he doesn't think it's important, or if it's obvious, which is where I look at it now. It's obvious of why that balance would occur. It occurs at the arithmetic level. And so I simply, it's hard to see my screen, so I can't really share it, but right here over to the left, yeah, I can't see any of it, but I'm just going to describe it. So I found a solution. I was able to kind of, with opponents, you see, I can see that the opponents are in there. The powers of offset powers, those are all opponents, and balanced his equation, and now he's got that balancing mechanism. Did he care? Not really. I mean, I didn't hear back. But the point is I can see I can apply this to different various models, even if they're those that I don't really agree with, because it's just such a useful tool from arithmetic, not been used before. So we go to the next one. Next slide, please. And so I started using it for problems that were significantly important to me. I'm interested in number theory, as I mentioned, and I was very interested in elliptic curves. And if people aren't familiar with elliptic curve, just think of it as a torus, a big old donut, and the L function of elliptic curve is something that was done by Haas and shortly after World War II, where he attached a zeta function to the elliptic curve. What that means is kind of like, if you don't know much about something, you don't know how it works, you can attach something to it to see how it handles the load. So for example, a tow truck, well, we don't know if it works. Let's put a load on it and have it tow something, and then we can better understand it. That's what Haas was doing by attaching a zeta function to the elliptic curve. And what you end up getting is this L function. And the L function of elliptic curve is super fascinating, again, in that the infinite series representation or their product representation doesn't converge for a real part of S less than 3/2. And so I said, well, I know how to fix that, and there I did. And the equation right there below, you just add some weights, and I'll kind of go over a little bit, and you got your if you can see, I can't show the cursors in the equation under 3, it has x. Yeah, to the left of that, a little more, right there, back. There's this x right before the second series. To the right there. Yeah, see that power 1 minus 2s. There's a little offset, and I add that's going to be the scaling factor, and the equation is so accurate to what the statistical interpretation of the L function at. Oh yeah, so why is this important if you're not familiar with elliptic curves? Because, well, what's most important about the L function of elliptic curves is value s equals 1, but that infinite series does not converge in the area, so you have to do all this fancy work to get around that problem, and you can use statistics and everything to determine the value at s equals 1. But you'll see my to the right, there's this little table that my value of this infinite series is exact to the standard values given off by the function. Why that's important is because this controls an infinity. It controls a singularity, and you can just balance the other side and give a very accurate value just by doing a couple tricks, which we'll kind of go over. All right, next slide. This all comes from the self-division. So really quick, I'll describe that function. Weights is not something that I came up with. I don't even know who first is. Maybe Laplace. So they're used to smoothly truncate the Dirichlet series, and I just won't get into it. But some function like e to the power of minus tm or something like that. So and you can have another one on the other, and basically you're weighing it so that they're equal, so that the L function still is equal in value, but we want it to converge at a rapid rate to stop that infinity from blowing up. And we do that with the opponents. All right, next slide, please. All right, and kind of this is what I was just talking to as well. We can skip this because I'm not going to deal much with weights, but that's one condition of the weights. You get, yes. So if you have two weights on each side, the Mellon condition is that they equal one. This is not new work, but it's just one way to do it. All right, go ahead. Thank you. And so the scaling factor x to the power of 1 minus 2s is the interesting thing is the exact symmetric rescaling, and that makes the 2 halves balance around that real part of s equals 3 halves, and it's that offset of 2 minus x, and kind of we'll get into that. But that's kind of what I'm doing, and just going through different problems and solving them in different ways. So let's see the next example. Let's see. Actually, I think I described. Yeah, this is just showing what the epsilon is. It's a plus or minus sign. All right, next slide. It's not terribly important. I want to get through the good stuff. So a little bit more on submission. You can see the symmetry with submission and exponentiation with division. So division of like bases. If you divide two like base opponents, you get, let's say, a base a and a sub m over a sub n, you get a to the power of n minus m, which is the exact mirror of if you were to do a to the power of m over a to the power of n. So a to the power of m minus n. So you can see the balance is pretty neat in that way. And next slide, please. There's a lot of these things you can learn. Oh, yeah. So it gives a lot of insight into uncertainty relations, which I do not believe to have to do with real uncertainty, but it's kind of where there's an inequality within a certain region. And I'll show, so what I was able to do is break down any uncertainty relation and show why it occurs, and the bounds can be defined from this alpha in the numerator. And I'll show that it's a quadratic. We go to the next slide. And so we have kappa to the right on that graph, and then 3 minus kappa on the left. And it's centered at 3 halves, which is expected. And that those points where the region of inequality begins, I think with this inequality, the region of equality was inside that region. But those bounds are the zeros of that alpha quadratic. And the distance, the magnitude between the uncertainty bounds comes from the discriminant of the quadratic, which is the square root of 41. And so there's a lot of things you can do where I can take what's the simplest probability of a coin toss, and if I know its initial angular momentum and a couple other things, then I can tell you with certainty, if you know how long it's going to be in the air, with certainty what it is going to be, heads or tails, which shows that it's simply not, there's nothing uncertain about it, there's nothing chance about it, but it's very deterministic in that way. So that all comes from this kind of same thing. Can we do the next slide? Skip over this because I just kind of talked about it a little bit.
Go to the next one.
Yeah. Oh, here, let's show the roots here. If you look at the roots, this is kind of interesting. There's kind of like these conjugates, and if you invert this equate those here says 2 over minus square root of 41 plus 3. And the other one, the other root is 2 over square root of 41 plus 3. Those are those bounds. The zeros occur at those. If you invert that, it's a very similar type of function to that which defines the oh, why am I drawing blank? 1.618, the golden ratio. So there's a so you invert that, square root of 5 plus 1 divided by 2. So I can tell you what that 2 comes from. This case, the 3 and the 2, it shows the center point, the 3 over 2. So if this were if we had an uncertainty relation that was centered on the roots were plus or minus the golden ratio, we could actually tell you where those numbers come from. The square root would be the magnitude around the space. And anyway, it's kind of just put a note over here. It's not terribly important, but neat stuff. All right, we can do next slide. Move on to something more important. Same thing. Let's skip this too as well when I get the other stuff. All right, so then we bring about something that's very important to me, and it was important to Jonathan Sandel, and who is a pretty well-known number theorist who passed away a few years back. And he had kind of come across with this how to determine if something is a rational number or an irrational number, a general principle. And he came up with part of it where it's in terms of the residuals, which we were talking about earlier, residue. And if the absolute values shrink, well, actually, kind of this combination to what I found. So I'm going to just say what he said. He says, if we can know these conjugates A and B, then we can tell whether C is rational or not through its residuals. But he never had a way to actually clarify whether or not what A and B was. Now with opponents and submission rules, we can actually apply them. So I'll go ahead and show how we do that. But first, I can do the next slide. This first came, and say what you will about this, but Greg and Deddy and I do have a purported proof of the Riemann hypothesis. It has been out for a handful of years, and I'm happy to debate it with anyone. But the issue is what we have found, the method, well, there was a couple things about it, but the final result comes from this rate of ratios, which is the absolute value. If you look where it says limit. So in this case, just to give a quick summary, this is where a lot of this came from, the origins of this principle before I show it. So the absolute value of the function on top and the absolute value of the function on the bottom, if their rates are similar, that is, they're both harmonic functions, or they're both factorials, or they're both exponential, then they're not mixed rate. So then at that point, what you're going to get is a rational constant at the end. Now, if it's a mixed rate, let's say we have an exponent on the bottom and something like a factorial on the top, or vice versa, and they converge at different rates, then we would say it's a mixed rate. They're incompatible. And if it's a rational number, it always goes to 0. If it's an irrational number, and we'll kind of show the proof of this a little bit. If it's an irrational, you'll end up with this constant, this residue. That might be pi, it might be Euler-Mascheroni constant. In this case, in the paper, it's kind of what gave me the idea to do this, is we had this neat thing, and it leads to the solution, that this rate, they converge in a very similar way, and it gives 1/2 always, no matter what, which leads to the proof. So that's a rational number. But that's kind of those, just, I'm not going to go on it too much, but the kind of inspiration behind what follows. All right, next slide, please. And the next thing that got me really bugging about it was this. And so the zeta function, we have the first term has into this infinity at s equals 1. So 1 over 1 minus 1 is 1 over 0. So the zeta function has no, it's undefined at s equals 1. But the second terms aren't. So the 1/2 plus I times this integral is defined at s equals 1. And the value comes out equaling the Euler-Mascheroni constant. And so the question is why? Why does it appear in there? We know, a lot of people know this. It appears in a lot of areas, but what is the Euler-Mascheroni constant? Nobody even knows if it's rational or irrational number. All right, next slide, please, and I'll show you. So what I did is I kind of manipulated the equation a little bit to get a different form, which I thought might be clearer. So it's the bottom equality, and then I'm just kind of showing how it came to this principle. And I'm looking at it, and I'm saying there's got to be some way to determine if this is rational just by this ratio. And eventually it did click, and it came about with help of Sandow's research, but also the opponents and the submission rules. And I'll show you how I applied it. Next slide, please. So it came from this way. So traditionally, the Euler-Mascheroni constant gamma, it comes from this limit. And if you look back to Annarithms, you remember there was the annarithm is equal to 2 minus the log of something. So there's some offset of the logarithm is what an annarithm is. And this is the limit of all annarithms. That's exactly what we're saying here. If we take this to infinity, we're taking the limit of all, and what is left over is Euler-Mascheroni constant. So it's very interesting that this is the residue after we burnt the wood of this operation. And so kind of give a little insight to how we can kind of determine whether it's irrational or irrational. And we can do this with any number. All right, go ahead and do the next slide, please. I'll show you how we do it. Because that was very interesting for some of the work that I was kind of doing is with the Birchett-Dyer conjecture, with the elliptic curves, the zeta function. They kept putting out these residues in this form. So they're all very similar. So for example, when you take the L function of elliptic curve at s equals 1, it's kind of like deflating an inner tube. It's flattened and everything kind of drops out, but there's some residue left over. And this is the value that was found in our paper, 1 over 2c times annarithm of 4 minus gamma minus 3. And k function, or the inverse, namely, which is a very important function in that paper as well, it's very similar, but instead it's the log plus gamma plus 1. Well, that's very similar to if you take all of the non-trivial zeros of the zeta function, a completely different problem, and take the sum of them to infinity, it comes out in the same residue form as well. And I said, that has got to be a pattern. And so what it in reality is what this whole thing is doing is reflecting the pairing of zeros. And so everything is reduced and it leaves this residue, and we can tell a lot about what the function is doing and whether or not it's rational or irrational. I'll show you how it's done. Next slide, please. Oh yeah, I should say beforehand, this is something, so with powers, there's something very uninteresting about this when you look at it in terms of powers. A plus B times A to 1 minus B equals A. It's so obvious that it's not even interesting, and I don't think anyone has ever thought to look at the equation and go, well, I'm just going to take A to the power of B and replace it and apply some weight or some factor of A. I'm going to turn it into this. But with opponents, you can see very good reason to do this. And so it has the same idea. A sub B times A to the power of B minus 1 against the mirror reflection gives A. And it becomes very useful. Go ahead to the next slide, and I'll show you what you can do. Is when you start to do Laplace type damping, which is kind of, if you take any Laplace transform, it has this this e to the power of mt inside the integrand. So if you can see it right here, and we're just going to swap that out with some opponents. And this is a little complicated. I'm just going to rush by it to show how to do it. But basically, we're going to decompose this integral, and then we're going to kind of get this varied form of the residue. It's not a Laplace transform of the residue. You could say it's kind of like a altered form. It's not the raw thing, but it's basically at that point with opponents, if you see the last equation at the bottom, the lambda, you have, oh yeah, and then go to the right. Look at all those powers. Those are all opponents. I just put them in power form. E to the power of minus n minus 2 to t. Can you take your cursor up to go to that equation, or down a little bit? Right there. That in that parentheses, there's 3 terms, A, B, and C, and their coefficients all have those Laplace type damping things. And so what we've done is actually is you can, if you kind of set it up this way. Now obviously the Euler-Mascheroni constant's a little bit more complicated than determining whether the square root of 2 is irrational, but this is how I did it. In the next slide. And there's the proof in one sentence. If we assume gamma, the Euler-Mascheroni constant, if you have those other equations all defined, if we assume that it's a rational number with having 2 integers p over q, and then you take and let z be as rational times the residues, and all those must be rational, and we assume that, then while the absolute value, which we're taking the residues, is less than or greater than all that, and that goes to 0. Well, if it should go to 0 eventually, but it doesn't, and therefore it's contradiction, and therefore it's not rational. It's that simple if you understand what some of the premise. But the point of this is that this is just applying the tool in one other way. I'll show you how now we do it with the square root of 2. Next slide, please. Square root of 2 is a bit easier. I can't really yeah, I can see a little bit if I stare. So we have the sundial kernel at the very bottom. We have the A, and those are opponents. A, the opponent of n, B to sub n, and those we're defining our conjugates. And then we go to the next slide. As long as we just kind of do this all day long, and we take that limit, which is the absolute value of lambda n to infinity, and then we end up with our proof again. So if it was an integer, if it was a rational number, then it would tend to 0, but it doesn't, and therefore it's irrational. And we can do this again with pi. This is where it really gets interesting. Go to the next page, or next slide, please. So we already know that pi and square root of 2 are irrational, but what makes the difference between them being transcendental or non-transcendental? And I know it's a little bit number theory, not outside of physics, but we can get into the physics end of it too. So do the same thing here with pi, and this one actually doesn't involve any opponents or submission rules, but it's just the principle itself. And it goes to 0, and so on and so forth. So therefore, it must be irrational. Here's the interesting thing. So if you have 2 mixed rates, this is kind of what I want to talk about with physics too. So if you have 2, let's just think of a circle. We start with the pizza, and the diameter divides a circle and into 2. So if we have a point on that circle where it's going to go, and we have 2 points that are travel. One's going to go around the circumference. One's going to go along the diameter. Those are mixed rates because one is cyclical, periodic, and the other has a beginning and end point. It's discrete. And so if you have this mixed rate, and where one is continuous and the other is discrete, that's when you get a transcendental irrational number. So the ratio between circumference and a diameter is pi, but the reason why it's irrational or transcendental is because that circumference is continuous and the radius is not. So now with square root of 2, why it is not transcendental is because we can do the same thing. We can consider the rates of corners of a rectangle, and so they both are discrete lines. They have a beginning and end, and we can get the value of the square root of 2 from that. But because they're both discrete, you're not going to get transcendental. So this is kind of just something that followed from. It's a separate principle. Yeah, it's not really involves submission opponents, but it was something that tool has yielded. So I hope that's understood. Is this is a tool that can be applied to any problem you really want to use it for, and it starts to yield interesting results. Can I see one more slide? Yeah, so that principle is plainly stated. Discrete rate mismatches generate algebraic irrationals, while continuous rate mismatches generate transcendental constants. So this is more of a number theory issue, and so obviously physicists aren't typically interested in this sort of thing. But what I would like to show is that there are a large number of problems, and starting to apply this concept of self-division to something that comes up everywhere in number theory and in physics and in biology is something that maybe people could start applying and seeing if it solves certain problems for individual models. Next slide. I think that's it. Yeah. So this is the takeaway. If you really if you're at the point where you're going, I don't see how this is going to yield anything. Do this. It's a simple test when you get off here. Take these 3 definitions, plug them into ChatGPT or Grok, and type in any question you want to understand, and just say, how would this apply to this? And it's going to pop out all sorts of answers for you, because we don't think in this way. But the difference is everything is new and thought in the same way for these LLMs. And so if you think of it as thought, and so it doesn't how would you say, prioritize in terms of, well, you've been using exponents all your life. Why would you need to do something in terms of opponents? It doesn't think that way. It immediately sees all of the new avenues and paths forward. And so I think this is the best thing. Go apply these to ChatGPT right here. You can take them and say, is there anything does this mean anything to you? Just ask it that. And say, is there any problems in physics or chemistry or number theory that this might be useful for? And you'll see it's going to give you like 10 right off the bat. Is that powerful? It's just that we have not used it. It's kind of like doing math without addition. We just kind of been working around it and ignoring it, and therefore we don't see it. I know because I went through it. It sat on my desk for my computer for 15 to 16 years, and I never saw the value in it. But the moment it clicks, then all of a sudden you can find a large number of solutions. In fact, most of the problems, and Greg Volk, I don't know if he's on here, he says this a lot, is that most of the unsolved problems we have today in physics and math all involve infinities, all involve infinities and singularities and these constants that pop up, and all of those are resolved with this process. And so if you're going, well, I don't see how it could be useful, it's like, well, then live with the infinities, live with the singularities. But I can tell you there's a lot more to see if you remove those singularities, because they aren't representative in most cases of what is really going on in nature. Maybe a black hole isn't a hole at all, which I think a lot of people on here would agree. And what if you had an equation that just kind of wraps nicely around the circumference of whatever the object is? And that's exactly what you can do with this, because those affinities don't arise. You place the you place your weights on both sides of that infinity, and you can reduce any of these problems. And it's nicely solved. So that's I hope as takeaway is take this information, take these 3 definitions, and plug them into ChatGPT or Grok, and with your work, whatever it is problem you're working on, or at least kind of just get an understanding of it, and you'll see all sorts of solutions are going to pop up. But if you're like me, not exactly a spring chicken, well, maybe take a little hard time to start thinking of math in a way that our brain wasn't trained at a young age. We were taught exponents and division at a very young age, and so we can do it second nature. But so you can use, if you can't start thinking in terms of opponents of submission and realize for what it really is, it is self-division we're looking at. We're not looking at exponentiation in a lot of these. It's self-division is more accurately describing it. And again, like I said, you could probably look at subtraction and describe it all in terms of multiplication or addition, but that's not really what the process is. So I would encourage that. I wanted to introduce it to you because, like I said, I'm getting more solutions than I can handle, and it's a little overwhelming. So it'd be great to see somebody else going out there. Oh, and if you don't like me, you don't want to credit me, don't worry. You don't need to. Don't even call it opponents, because it all reduces back to exponents. So solve it using the opponents, and then in your work, just kind of say, work it back into exponents and show it in the way. You don't even need to, in your papers, don't even need to introduce any new math. Just use the tool on the back end in order to kind of, get the solutions you want. Because I'm telling you, they're coming fast for me, and any one of you guys can have it the same. So thank you. That's pretty much it. I'd be happy to discuss it with questions.
Right, excellent. Let me try to get out of this so we can get back.
Yeah.
Escape does it, yes. Now, close that. Get back to the session. I'll stop sharing my screen. Stop screen. And you're back. Now, actually, in going through the slides, I found it very, very useful, but unfortunately, I have not had an opportunity of looking at the questions. So maybe if you just give me a moment or so, I'll just check are there any questions. Just maybe before we get to those, though, there's a comment I might make myself. I found this actually quite fascinating because Jeff had sent me these slides, and I did take the liberty of going through them very, very quickly. And they were pretty, I don't know, Greek to me, if you like. But actually, I found his explanation very, very clear. And he's elucidated a lot of matters for me. I think a lot of us will be interested in how, for example, he gave an example of applying it to the UV catastrophe and, extracting the sort of Planck amalgam of the classical curves for low and high frequency. I just wondering, by the way, Jeff, before we start the questions, you went, or I think it was actually the first level was the exponentiation, the repeated multiplication. I'm just wondering, can you go to another stage, repeated exponentiation? I've forgotten the name for it, but there's a name for that, isn't there? Process where you can have repeated exponentiation of quantity.
Yes, yeah, you're right. I'm drawing a blank on the term. It's like x to the power of x. Yeah, that would be the next in line. A little advanced, but there are some mathematicians using it. Yeah, but I have seen some of that. But no,
it seems very, very powerful. I'm just actually going through the questions now to see are there any specific. Okay, see again, they're not quite sure what some of these are. Because I think a lot of us, I mean, even people who are interested in physical science and are critical thinkers, were frightened a bit by mathematics, and I think that's a shame, because a person like Jeff, who has a comprehension of this, has basically another sense. He's able to get to the nub of a lot of questions. Okay, just
I think there's one comment in here that looks like a question. Most of them are not, but there's one. Let's see, where is it? So the gist of the theory is magnetocosmos. For the
I'm looking at magnetocosmos as well.
Yeah, it's the only thing close to the question.
Okay, the gist maybe of the theory is that A dan R equals E, and for which you use, it's a question mark, for which
he's asking, is this equality the general operator? The answer is no. The operation is repeated self-division, the same thing as repeated exponentiation. It is the exact inverse of powers. Instead of raising the powers, we're subbing something to the opponent.
And you could keep on going ad infinitum, actually.
Presumably. Yeah, exactly. And so there you can kind of combine a lot of different things. So the answer is no, that single equality is not the gist of that. In fact, that was only how you would reduce the repeated self-division to powers. So that is a power, but whenever you see these, something with an offset inverse, in the power, you could actually say that's not an exponent anymore. That is an opponent. That process did not get from repeated multiplication. It came from self-division. And self-division is a different process, and the graphs look different, and so on and so forth. So when you do understand it, there you go. Yeah. Is this another question here?
The next one might be a statement. I'm not sure. It doesn't seem to have a
It doesn't
question.
seem a question, so I don't know.
If it makes sense or not.
Let's see what it is. No, so he's using powers, and my thing is to stop using powers. And when you're talking about self-division, so I don't know what he has here, but I'm interested in looking at it in terms of opponents and submission. So anytime where there's something anymore, whenever I see something in the power offset and inverted and reversed, which is 2 minus x or x minus 1 or so on and so forth, I'm now looking at that as terms of self-division, because that is what it is at a basic arithmetic level. So.
By the way, your colleague Greg Vogt, who has been involved with the society, in fact, he moderated the session some years ago, is here. So he's happy to what they're saying.
Maybe he has some comments if he wants to jump on. Does he have a mic?
So I'm almost finished the main questions. He's reminded both of us it's tetration. Neither of us could remember the word.
Tetration. That's it. Thank you,
man.
Greg.
Thank you.
Very good.
Greg, thank you.
Yeah.
Tetration. Yeah. I don't know. There's
so
one.
That would be a higher order operation. So this one,
right.
It fits below exponentiation. So it's kind of in order of operations, it would be there. So it's kind of like this missing piece. You could probably extend it and keep doing now. What would be the equivalent of tetration with self-division? I don't know.
I know.
Yeah, so keep going.
But it's funny, we weren't really taught. You mentioned earlier on, we were taught these ideas, and you have to think. But we were taught exponentiation. We were never taught tetration.
Exactly.
School,
yeah, I dabbled in it. I looked at it a little bit, but I didn't really see until there may be one day where somebody says, okay, this tetration only solves these problems, and maybe there are some areas where we are, but right now it hasn't come up a lot in my work. I haven't seen the need for it. I have seen the need for self-division. It comes up a lot in exponential decay, propagation of signals through a medium, all sorts of electronics and physical processes involve it. It's so common. You look at any average equation, if you just pulled up 100 equations from the physics books, you're going to have a good 10 to 20% of them are going to have self-division in there. You're going to see those powers with the offsets and inverse. So.
Okay. So just maybe one last question before we get to the discussion.
Yeah.
He's asking, would you think that this mathematics could help in an example such as the following? If two spheres equal charge touch, the distance is 0, but the distance for the center point is 2r. This evolves into the problem of calculating Coulomb force at quantum scale. Do you think this might be of any use instinctively? Your ideas.
Well, here's the fun thing. I'm going to copy it. Let me see if I can.
Yeah, exactly.
I'm going to paste that in ChatGPT. I bet it comes because I have a all right. I have a
well, you have access to the questions. You can copy and paste them. I'm just going to look at the private chat now because I haven't looked at that either.
Yeah.
Okay. We just have James Keane. Bring him in the moment. What is self-division as well? Yeah. Okay. So in the green room now, Jeff, we have my co-host for the alternate Saturdays, Roger Anderson. We had Dennis Allen, who also is one of your collaborators.
Yeah.
We'll have a number of things to say. In fact, actually, I might say, just for everybody's notice, that Dennis put me in touch with your good self. So I think that's why we have you.
Yes, that's
Thank
right.
you very much. And we have James Keane and we have Cornelis, who is actually blank at the moment. I think he's going to come in at the moment. I couldn't see his video even. So if anybody would like to come in at this stage, if not, I will bring you in. For example, James Keane has already asked a question, what is self-division? Would you like to put some questions directly to Jeff, Jim, or maybe just give me your attitude? Jim has worked on binary mechanics, and in fact, he's given a number of talks on that. I think he's giving a talk tomorrow to Harry Ricker's cosmology session held on Sundays. So
Yeah, good to
Well,
meet you, Jim.
hello. Actually, I don't have many questions. I did ask what is self-division, but that's right at the beginning. And I don't think I really followed what really the whole talk was about very well. So I don't have any particular question beyond that. Thank you.
do
You're
you
welcome.
think, Jeff, just before letting you go, Jim, do you think, Jeff, any specific reference to one of your papers, maybe on ResearchGate or something, would be useful for people such as Jim or myself or anybody else?
Yeah. So, Introduction to Annarithms Submissions is the first paper up there. Ultra simple. It doesn't have any other applications. Just shows the basic groundwork. Really, what I think is the best thing to do: download that paper, copy and paste it into ChatGPT, and it'll summarize it in any way that you uniquely want to learn it as. But there are three. If you remember that screenshot of the three definitions, that everything can be described in terms of that.
Well,
And
if you're
so,
using GPT or Grok or any of these AI things, it indicates to me, but this is my own personal approach, it indicates to me that you're looking at the past.
my
And the past
recommendation
is
is
that
that you would
space and time are continuous. And I feel that those particular axioms are now obsolete.
I'm
Okay,
not
there are
sure
2
what you're
points there,
saying.
gentlemen. One was the efficacy or otherwise of using an AI system to summarize it. The other is this point as to whether space and time are continuous or not. So I don't know if you want to say a word about that, Jeff, before we.
No, I haven't talked to or presented anything about space time at all.
Yeah, because that's another aspect which we've talked about, and it's inherent in Jim's theories. But with
Yeah.
regard to the summary, I downloaded a paper which actually Dennis Allen and I are discussing
Okay.
with the person who wrote the paper, and he's going to give us a talk next month. But I didn't have to do anything about that. It just said, this seems a very long and complex paper. Do you wish to have a summary of it? So I just pressed a button. I don't know what tool it used. It wasn't ChatGPT. I don't know what it was. It might have been some other AI. It gave me a summary of it, which is of some use anyway. So thank you very much, Jim. We'll
See you tomorrow.
We'll see you tomorrow. Yeah, I'm hoping to go to hear you speak tomorrow. Thank you. Okay, now, so I'm sure Dennis Allen has something to say about this. Denny, we couldn't speak to Denny, unfortunately, for a number of weeks, maybe months, because he had a rather old computer system. And this StreamYard system, I just tell you, is rather sensitive to being up to date with your operating system. And, he was just inaudible. So I've just tested a system before we went on air, and he's perfectly audible today. So, Denny, I've taken the liberty of putting you up because you've been a contributor to, or a collaborator with Jeff and Greg as well on some of this work. I think you have some videos where you've discussed a lot of these issues. And you are a mathematician as well, actually, which is quite important. So have you anything to add, or you maybe supplement or disagree with or ask?
Well, I have a question for Jeff.
Yeah.
Very good.
You say that Planck had to introduce quanta in order to get a theory that was accurate. But if, in view of what you said, maybe quanta aren't necessary.
Not necessary for this problem. I think in terms of something being in a nice unique packet, or thinking of something even in terms of a particle or anything, is very useful. But I don't know if it represents the way reality is. So I don't know. I can't see that small. So I don't really know. I definitely know that I really, when working with the hydrogen atom, I'm really, it gives me a great insight to use quantum numbers. And so I'm constantly, I like that it can reduce and down to that. It's very useful. I just don't know that nature thinks in terms of integers. And maybe it does, but I just somehow I seem, and the more physicists start trying to break apart what they thought was a fundamental particle, seems to be something more fundamental beneath it. And I'm just wondering if there's even such a concept of the particle at all. And I think quanta kind of falls in line with that. So I definitely think it's a useful tool for modeling how physics works, but I'm not sure that it is a real thing.
Well,
And I think
Planck was the same
Max
way,
Planck,
actually.
might have thought along similar lines.
Yeah, he
because
did, actually,
we've extrapolated it a lot to say quanta are fundamental and so on and so forth.
Mm-hmm.
But I think his conception was, look, this conception seems to work. It seems to give the laws, but you know, whether it's actually a real fundamental aspect of physical reality is another question.
Exactly. That's the way I feel about it. It's
From
not something I want to get rid of. I think it's very useful in modeling. It's just whether or not it represents nature, I don't know. In a way it does, because it provides solutions. So in that way, it's a mathematical way, and that's kind of what physics is anyways, where it's a mathematical way of describing the universe. So it's kind of all abstract, you know, concepts describing the way the universe is in the first place. So I don't mind it. It's just that I don't know. I think there's certainly signals, or it can be thought of as wave packets, and so in that way I could think of certain pulses could be thought in terms of a quanta. So it's not that I don't think that they don't exist. It's just that yeah. So I don't know. I think that it's more of an abstract. I think in the end, eventually, what's going to come out is it's going to seem more abstract than actually representing reality, but useful, but abstract. Cool.
okay, thank you very much.
Yeah, thank you, Denny.
Oh, okay, well, thank you very much, Denny, and we'll no doubt be able to talk to you a bit more about this in the future. So I think Cornelis is gone, actually, but I was interested, by the way, Jeff.
Mm-hmm.
It just seems to work out. I don't know what you called it. This sort of reverse reflection, where you get sort of like n minus m, will you get m minus n, that sort of thing. How that worked out? I wonder, is that a fundamental thing coming out of the asymmetry of the system or something?
Yeah, it comes because it is like subtraction is the opposite of addition. Self-division is the opposite of exponentiation, and so that's why you're getting the mirrors. So it would be the same way as there's this duality between these two operations. That's why I think it's so important that we start considering it, because it's there already. It's just we're ignoring it. And you can see it's there because there's a mirror reflection of exponentiation in it. So we can, it can be reduced. Any problem with exponents can be reduced to self-division. Any problem in self-division can be reproduced with self-multiplication. But in reality, what we're talking with exponentiation is growth. And when we're talking about with self-division is decay. And not exponential decay, but I mean more like contraction, not growth, but contraction. And so they're one balances the other, and it's all over nature, and you'll see it with the physics, equations and laws, and maybe most of our physics actually is pretty solid and ready to go. But occasionally we run into these little problems with infinities, and one of them was the ultraviolet catastrophe, where the equations just didn't work. They didn't describe nature exactly as it behaves. And so in these cases, it's very important to say, well, why am I not looking at self-division in this problem? And then you'll see it becomes very easy to resolve that infinity.
Yeah. So, by the way, we have a nice comment here, which I put up because I'm always concerned that a lot of ideas which are coming out are bereft of exact mathematical analysis. People are just, talking and using language. So anyway, we have this from Tomido Cal, who has talked to us, actually. He says, very original thinking. thank you for this presentation. So thank
You're
you.
very welcome. Thank you.
Yeah, it's important because, we could easily get people saying, you're just, pontificating and it's beyond me. And I don't understand any of that. It's double Dutch to me. Sorry, Ido's a Dutchman actually, or it's Greek to me. Anyway, so there you are. Okay.
I think because it's easy to understand at a basic level, but very easy to ramp up into very complex problems too. So it kind of, it's a useful tool. It's like I'm offering a hammer. You guys can continue to use a saw, put a nail in, or you can actually apply this tool for where it's useful to your own work. So I just thought it would be important to kind of get it out there and offer it up and have fun with it. And
en passant, you did mention fundamental constants which appear in nature, in the whole structure of nature. Things like the golden ratio and the Euler-Mascheroni constant, things like that. So I think that there's a lot of fruitful work that could be done flowing from that. And I think maybe you've sparked some ideas in people. I'm going to look at this in more detail anyway myself later on. And I hope, by the way, the acronym RIP was unfortuitous,
that's kind of like saying math is dead, AI is going to be taking over anyway. So no, rest in peace. No, it's just a coincidence. Yeah.
Right. May I ask, by the way, are you currently employed in the academic area, or are you?
No, I'm not involved with academics at all.
Yeah. Okay. So you're really an individual researcher.
Yeah, exactly. Yeah, like most of
who have been involved in the NPA. You were probably here actually before I was.
I stepped in some of your guys' calls. Some of your Saturday mornings, I get emails all the time for it, so sometimes I do. But
I thought your name was familiar, all right, and I even actually took the liberty of searching some of the conferences, and I couldn't find them. I couldn't find that you talked before, but that's probably because of the disjuncture between the NPA and the CNPA.
I think so. I presented at Maryland NPA, which I think it was before it was called this, and also in New Mexico when it was joint with, they teamed up with Tesla Tech.
Oh, these are face-to-face conferences.
Yeah, face-to-face, and then there's about 4 or 5 Saturday mornings I've done. Yeah.
Okay. It's a bit of a problem actually, which some people might be criticizing us with regard to, and I think it's possible that we can resolve it in some way. If you go into the John Chappell YouTube channel, you get a lot of stuff, and you get the most recent talks, and then it seems to disappear after about a dozen talks. I tried searching for Jeff Cook there, although maybe is Noel your middle name or is your first name? Maybe
my middle name.
I got Jeff Cook, and I only got today's conference, so I don't know what that was. There's another man, Kev Con, whom I recognize. He's a very welcome analytical mind who tends to be a bit more mainstream, if I may say so, without criticism. And he has a question here. So let's just put it up, if I may.
Yeah.
So Kev has said, Planck's breakthrough wasn't mathematical, it was physical. Instead of modeling energy as continuous, he tried describing it discretely. Yeah. Well, that's basically what the point I was making. I think you agreed with. He's looking at these sort of harmonic oscillators, which are effectively operating in this way, and taking the integer times the basic energy, h nu. Yeah. Okay.
There looks like there's a I agree with that statement. There's a question coming in. Did I get an answer for Ido's question? Yes. So the question it kind of mixes 3 different notions of distance, with Coulomb's law. But it doesn't really, I wouldn't say it kind of carries over too much to submission and opponent ideas. My framework's not about particles, but it's rather about how operations behave when like scales invert or collapse. And so that's kind of what's happening. So I hear ChatGPT is kind of saying something about that if you take a classical Coulomb force as an opponent dominated law, force of R equals k times charge 1 charge 2 over r squared. As r goes to infinity, the opponent term r to the power of minus 2 blows up. This assumes unrestricted exponentiation. There's no built-in mechanism that limits growth. So this is mathematically clean but physically naive. So you could think it's saying here submission encodes scale reversal. I'm not sure what it's saying here. It encodes turn suppression when the scales collapse. Yeah, but it doesn't. Just answer your question. This is the important. It doesn't derive the true Coulomb interaction at quantum scale. It doesn't account for virtual photons, vacuum polarization, spin. That domain's still quantum electrodynamics, not operator algebra. So now, if you have a particular equation, something, like give me an example. Let me see if I'm gonna get an equation. I don't know how to share it. Let's see.
Yeah, we had difficulty. You're sharing.
Yeah, let's get an example.
If you put it in the chat, maybe.
Yeah.
There is a private chat as well, but not everybody can see that. But I can see it, and I can put it up.
Yeah, let me do the chat. See if I can get something. I'll get a couple examples here. Really exponential relaxation and response laws fit very well. So RC charging, discharging, that's a near perfect fit. So let me throw that one up. Here, I'm going to get it in plain text. Could I get...
I don't know if Magneto's just asking the terminology. Why a down arrow?
Yeah, so I didn't want to. I like sub is a lot better. Underscore or sub.
Yeah, you gave.
So both. You can use either way. The reason why I don't use that. The reason why I don't use that is because there's so many functions that I use that have a constant variable and
could be ambiguous.
Continuous. Yeah, and I use the sub for the constant. And then in the parentheses, the dynamic variable. And so I use, where do I comment? So yeah, here we go.
Okay.
Go to, paste this.
By the way, the Shockwave is asking, but did you see Ido's presentation? This was on atomic structure. Maybe
no, I'm sorry, I missed that.
Yeah, well, if you have time, it's
yeah.
System.
All right, let me go to see. Maybe I could paste this comment into YouTube because I'm having a hard time pasting in the StreamYard
or into the chat.
I pasted it. For some reason, it's not pasting. It's really weird.
Don't see it.
I'm doing it. Here we go. It's going into.
Comment or chat. Where's it gone?
I'm going to. It's too long. I'm gonna paste it. I'm gonna paste it on YouTube because I have YouTube open. Let me just kind of do it in two parts.
Where in YouTube? We'll have to
on your live stream.
Well, that's what I mean. In the comment section, it says post a comment. You can just put it in there.
I'm gonna do that right now. Hold on.
Yeah, excellent.
Yeah, right, I'm gonna do it.
We'll all see it if you.
Yeah, I just didn't have it open. It's saying too many words.
Oh.
I have to paste it into like 3 parts then.
Well, I mean, if you've gone to a lot of trouble live, if you really want, you could just post it to me as a Word document or something, and I could put it up again. I mean, it would take a few minutes to do that.
Yeah, I'm just going to read it. I don't think there's a reason. Here I'm just going to read it because it's not even that long. Opponent anarhythm fits best with physical systems governed by exponential response or decay, not force laws. Good examples are RC charging and discharging, radioactive decay, Beer-Lambert attenuation, and Arrhenius rate laws. I don't know how to say that. Arrhenius. And in these cases, in these cases, the exponential describes the system's response. opponent behavior, while the inverse question, how long, how far, how much input is needed to reach a given state, is logarithmic, which is anarithmic behavior. Submission naturally represents scale reversal and bounded growth in these systems. It doesn't replace quantum electrodynamics or Coulomb's law, but it provides a useful mathematical language for exponential relaxation and threshold-driven processes. So that's the AI summary of that question. But so I hope that helps. Maybe not.
Yeah. Okay. Well, he's saying Ida's model we could talk about, but actually, if you won't get angry with me, I was thinking of giving you a real difficult question now.
Okay.
Very general. Not specific.
Remember that this is new to me as of this summer, so I'm still learning myself. I'm still a student of where
but
I'm
it's
to go.
more. It's a very general question, actually, in a way, but may not have a simple answer. Although your views would be valued. You've developed a system which seems to have great merit and has great promise, actually, for further development of physical theories.
Yeah.
But at this stage of your thinking, you've gone into a lot of these analytical tools. Do you think, bluntly, do you think that the current state of mainstream physical science, the basic theories of of the microscopic and the macroscopic, and the way the Big Bang, the origin of the Earth, and the way they're dealing with atomic processes and relativity and all that sort of thing, do you think that it's largely on the right track, or do you think it's very, very much faulted? It's in great difficulty at the moment, as many people do.
Yeah. So with all of these infinities, these are the areas where people are struggling to explain, and they're using it to describe things in nature that they claim are real, like infinite amounts of energy in a black hole, and then uncertainty relations actually say anything to do with whether or not God throws dice, whether he knows that throws them into places where people can't see them. All of these are interpretations of problems in the math. So all these infinities arise from a lack of understanding of how to get around these, and this problem will resolve a lot of those. The biggest problem I have with where physics is going is they're trying to explain, give meaning to these concepts that are meaningless. And a lot of the infinities are meaningless. There's even a lot of number theory problems where they have what's called irremovable poles, and I just don't believe in irremovable poles. There's got to be some way around them, and I suppose that's just because we're lacking some mathematical meaning. But in physics, it's very important not to do that, because even if we are lacking some of the mathematics to describe it, it doesn't mean that nature is really operating that way. And we have seen enough examples where physics was wrong, and they all kind of seem to be centered around these same sorts of problems. And so we need to stop attributing physical meaning, and trying to make predictions of the way the universe operates when it's a mathematical defect. And that's what I think a singularity is. I think that's what infinity, these problems are. Another example, it would be uncertainty relations. Another one, in my opinion, is also Einstein's speed of light as being a limiting velocity for anything other than light. I think you're going to have a lot of problems with that. And the same way that they generally believe this to be the truth, that it would apply over to the sound barrier. And they thought that the plane would actually explode when it crossed the sound barrier. And because the math is pretty much the same between the sound barrier and light. Well, just because this light travels at the speed of c doesn't mean matter can't, or something else might be able to travel faster or slower. And so then Einstein or whoever starts to apply physical meaning, saying, oh, well, that must mean that nothing can go faster, and therefore we have to describe the way the universe works in this way. but it's really just it's clearly a lack of misunderstanding of what the mathematics, and we know because we've seen it, this play out over and over again. So I would say it's not in good shape, but I think there's some very, very simple solutions to things that would really benefit our world if we'd stop messing around with what would you say? I just think there's a lot. I myself have discovered a number of properties of electricity magnetism not described in the literature, and I've made patents, and it's funny when the patent office comes back and I say, well, nature doesn't really work that way, and so we can't accept it. I'm like, oh, would you like a prototype? I'm selling them. They're working. Like, oh, you have them already? They're working. Yeah. So they're questioning things as though it's not even real, because the physics currently doesn't explain it. But so I would say the direction is not very good. But then again, at the same time, it was this way back in Galileo and Newton. The questions are the same. People are skeptical, and they have an understanding of what the math is telling them, and they're inflexible until the moment they're proven wrong, and this happens. And so I don't know. Right now, I would say it could go faster. I think experimental physicists are the way forward. Inventors get out there and making things and prove the physicists wrong. Not that a physics is wrong in all ways, but when they say things can't be done a certain way, I'm always questioning that. It's like, no, it might be. So.
Well, it's right. By the way, Magneto is asking, do you admire or you have heroes of Ramanujan and Nash?
John Nash, particularly, yes. John Nash, I really like governing dynamics. So he's is especially for you could apply to anything. Particularly in terms of business, and so like the concept that's most interesting in governing dynamics is in nature you'll see successful systems when there's no competition and no fighting. A bee will come towards a flower, another bee comes in to meet it, one just kind of moves to the other flower, and they don't fight over the flower. They don't have time. It's less time to kind of spend on any one given flower. Same with pigeons. If the pigeons messing with the food, if there's a bunch of seeds on the ground, if one pigeon starts to go after the seed, the other pigeon instinctively turns away from it and goes to another, because it's inefficient to fight over the single seed. It's so much faster to kind of go. And I really like that when you start applying that to economics and game theory. So I like, Nash.
Yeah, okay, that's interesting.
I don't know about hero, but I definitely like his work. I like his work.
Again, Shockwave. I think what he's saying here is he's saying, can there be a problem that people don't get results which they're claiming to be the case from observations, but since the mathematics says it's possible, they then jump to the conclusion that it is. I've rephrased what he says. He says,
okay,
yes, they make so many things up from observation that aren't real, but their math says it.
Yeah, I understand. Yeah, so I understand. I mean, I've had a number of things. So you got to have a plan, right? And so that's what a physics model is. It's your plan. But nature may have other plans, and so you got to be ready to adapt and change if something doesn't work out. So I definitely think we need more experimental physicists. A lot of people don't like to work with their hands, but the reality is that's where it comes down to is just grab a couple magnets and start playing around. Get dirty and make some electrical circuits. I can't tell you how many things I was absolutely
certain. Yourself, you said that earlier.
Yeah, I definitely, many times where I thought for sure something would work and it didn't as expected. And then what happens? You go back and you tweak a little bit and go, now I see what's going on. And then you go do something a little bit more interesting. So the progress is going to be made by misunderstandings. And so it's okay that these models are wrong. But if we hold these models as scripture, we're setting ourselves up for disappointment. Yeah. because they're gonna have holes. They're gonna need to be modified. So, but experimental physics, I mean, if something works and you keep reproducing, I mean, that's just the way nature is. And then you go. That's when I think that the model becomes useful. I mean, that's what Maxwell did. He didn't come up with this theory first, and then Faraday followed it, and then he started experimenting with it. Faraday is playing around with experiments, and he got doing something strange, and is moving in a unique way that he didn't know. And Faraday came in, or Maxwell came in and put equations to it. That's really historically what's been leading the greatest advances in physics. So Newton, observed things in nature. Then he went and applied his math. And if he couldn't observe it, he just didn't put it down. So
it seems to be, in a way, if I may say so, a bit of a distinction between classical physics and modern physics, what we might call it. Because I think you said, these things have been happening earlier on. You said that. But you see, you've given two very cogent examples where classical physics started from experiment and then built mathematical models on top of that. Whereas in modern, I'm talking about physics, since 1900, I'd say, very roughly. The tendency has been maybe the other way around, to go to an arbitrary. So.
Absolutely. Not only that, but they're describing things that not only can't we test, but nobody could ever test. Like strings and stuff. It's like, well, okay, well, how do we know if these strings are real? We can't.
The Karl Popper principle.
So this is kind of a problem. Kind of a problem is that we're now describing the way the universe works by things we can never observe. That's really unusual. I think there's some usefulness to that. So if we know certain things work with, let's say, electric field and the B field and A field, we can start to kind of break it down to more fundamental fields from what we know of those fields and bring it down to a logical explanation of the very fundamental fabric of space, if there is such a fabric, which I don't believe there is. We can do that, but string theory begins with an assumption that there's a string, not that we're deducing it to something causal. So,
there's no a priori experimental. I mean, Stefan Gift just says yes. You've described the scientific method when you mentioned Maxwell.
That's we should return to it. I mean, there's no reason we shouldn't. It's not. I mean, I know natural philosophy is what physics used to be called. It was a philosophy, but it was really it began. So it maybe in a way that was studied before the scientific method was really kind of formulated in an official way. But the reality is still the same. Is they didn't dream. They don't want to go. I mean, a lot of modern physics is just describing one's dream. This is the way I want the universe to work, and I don't know that it always does that way. Like I said, as long as it's falsifiable, I don't care what anyone's saying. It needs to be testable. If it's not testable, then I'm not really interested in studying it, because I'll never know either way. So it's like a dream. Could it happen? It could. Maybe it didn't. So.
Well, Jeff, the time has come when we want to leave just a couple of minutes for you to summarize, and then for me to come back and officially close the meeting. Okay. And there is therefore time for one more question, if there is any. I just want to, rather than cut it off, there's only time for one more question. Does anybody have a question in the green room or a comment? Jim again has talked about what happens if space and time are not are not continuous and are discrete. Well, that is the other subject which we can talk about, but it's something we always agree on.
Not really part of this subject matter, I think.
Yeah, exactly. And Shockwave just talked about microstring theory, might be connected with Birkeland currents and electric universe and all these other things. So, okay. Well, I think what we might do then, since we've only 5 minutes left, is I'm going to give you the floor. One more. What are you saying? Here's another thing from Stefan Gift. Let me just see what he says, because it's relevant to. Unfortunately, today Lorentz invariance has been imposed on all physical models, and this, I believe, has inhibited the advance of science. Well, I'd agree with that. Lorentz invariance is considered a bit of a dogma. Okay. Well, look, I'm going to give you the floor again. You can have as long as you want. If you want to take 5 minutes, 6, 7, 8, 9, or you want to say 1 minute. You've given a very comprehensive presentation, but you may be prompted to add to it in the light of the discussions and maybe talk just for a moment or two about what you think might be the best way of advancing these ideas in future. And then when you're finished, I'll come back and officially close the meeting. So is that all right, Jeff? I'm going to give you...
Yeah. So I've thought a lot about... I've thought a lot about this, and I think that with something like this is not going to catch on very easily. I don't think that there's anything new. It would take definitely a younger generation learning it in schools before it ever is put into practical application. But I do think that mathematicians and physicists, it is very simple, and so anyone can start applying it. And even if you don't think it naturally like you do, your standard models, the way you're working with the tools you have already, just really use an AI model to help explain it, kind of go over it and enter your work and enter the definitions and see how it might apply. And you'll be surprised of how fast you can get results with just using, it's kind of like AI to me is like kind of like a calculator. There's no shame in using it to solve math problems that it can do faster than you. And so, kind of throw it in there and say, how might this apply? And then kind of tweak it with your own. But I definitely think if you are stuck with any particular problem, or there's any problem that you really want to solve, I would immediately go ahead and see if there's anything applicable. It's certainly only as useful around infinities and balance and some of this aspect, but you never know. There's no way of knowing all of the different ways it might be applied. I found a variety of different ways to apply it, things, just recently. So, and then also may give you new insight. Like I said, the rate incommensurability principle came from it, that I didn't know that solution would be useful in other ways, completely removed from the basic arithmetic. So use it, and I definitely encourage, just maybe even an hour after this call, just kind of go and plug it into ChatGPT or Grok and play around with it and get an understanding. So even if you don't fully understand it, just go back and you'll see on this video, that last slide, it had the 3 fundamental rules. Just go ahead, do that, or go to ResearchGate and look me up there, Jeffrey N. Cook. But you might be able to do type the word Annarithms, and maybe it comes up in a search, and just get the paper and just copy, just open the PDF, control all and select it all and paste it into ChatGPT and start getting to work. And then if it starts to feed your creativity and you start finding other solutions, then definitely have fun with it. But you don't need to, like I said, you don't need to credit anything with me. You don't need to reference it, because anything you do find, it's going to kind of, you can convert it back to exponents, and so you don't need to worry, I don't want to kind of cloud my new work with some new math. You don't need to. You can reduce it back to exponents, and it's a tool. Like I said, it's a hammer, or when for putting in nails. If you want to use it, go for it. I'm just trying to get it out there because, like I said, it's given me more ideas than I can handle, and I don't even have time for it. So hope that you guys do it, and good luck. Have fun.
Well, thank you very much for that summary, and indeed for the lecture itself. It's my pleasant duty to summarize, or really to offer our sincere thanks to Jeff for having given us the details of this very interesting operator that he has come upon. And I think he's a very good expositor, actually, because the mathematics can be a bit difficult to grasp, but he's explained things reasonably well in the hour that was available to us. And thank you very much for that. And thank you. We now have a permanent recording. And thank you very much for your contributions, for your encouragement, basically, to use AI, plug in maybe the system and apply it to your own ideas and see whether anything comes out of that. There's no harm in doing that, as Jeff says. So I found it actually very fascinating. And thank you so much for giving us this opportunity to listen to you. And we can do further research by looking at the papers. The video is available now, so I'm sure people will want to go back and maybe look at some areas and maybe pause it and have a look at the slides. So that's available. And actually, I dare say that in the light of further developments, maybe of your own ideas, and maybe some other people looking into this in more detail, maybe even myself, we might want to talk to you again. So, you'd be very welcome to come back to us at a later stage and give us an update on the developments from this operator and indeed your other work in mathematical methods in modeling physical systems. So thank you once again. Unfortunately, the time has caught up upon us and we must end the session now. But I'd like to express the thanks of the CNPS for all your contributions, the people who've participated through Facebook and YouTube, and the few people we've had in the green room today. And last, but of course not least, our speaker, who's gone to considerable trouble to explain to us something which, on the face of it, is actually quite complex and is not simple, but is logical. So thank you again, Jeff, and I'll wish you all, wherever you are on the earth, goodbye, and every success in pursuing this and other aspects, looking and delving into the intricacies of the physical world. Thank you very much. Goodbye.